Follow along with me as I dive into this exponential function behavior Desmos graph. You can find a link to this graph in the companion document in the YouTube description, as well as inputs for these folders and the transcript for the video. Let's start with this first folder, this exponential growth and decay. You can expand that folder and see everything that's inside. And the way we can graph everything is just clicking that circle to the left of it. You see now it turns into a folder icon, and we've got some graphs that showed up. Because we're looking at sort of a standard window where x goes from -10 to 10, and we also, I'll note, have a square scaling, which means we go from 0 to 5 in the same distance on the x and y axes. This is kind of a home zoom that we're looking at. This won't really allow us to view these functions. Looking in at the inputs, you might spot this g of x function has an initial value of 100 and then an exponential growth rate. The d of x function will be a decay function, also starting at an initial value of 100. When I say initial value, think of that as the y-intercept. We plug in a value of 0 in for the exponent, and this is all a constant because r sub g, our rate of growth, has been defined. So we've got a kind of a whole process here of inputting a defined growth rate or decay rate, r sub g or r sub d, each limited to a range of values, or I should say a set of values that make sense. A growth rate will be bigger than 0. I set it to be a step size of 0.1 just so we can kind of go by 10% there. And then the decay rate is negative. You could definitely arrange this differently using a minus in the function to represent that decay, but I've just built it into the rate itself, just a design choice there. So r sub d is negative 0.5, negative 50%. Think of that as a 50% drop every time we move over 1 unit on the x-axis. And that range, it can't be below -1, because imagine putting this decay rate into the function. We're starting with 100% and we're taking some away. So if it's 100% minus 100%, that's just a constant 0 function. It never even hits the y-axis because it's just 100 times 0. So that doesn't really make sense. We need really a decay rate that's above -1, or from -1 to 0. I couldn't change this. It's actually set to less than or equal. So we will have a situation. I can drag this slider all the way down to where we just set it to be a 0 function or a horizontal line at y equals 0. Any other value in this range is going to work fine. Now let's find a way to view this a little bit better. We could zoom out and that might help, but then because of the square scaling, we don't really see the definition for the x-axis there. We really want to zoom in x only. You can open up those graph settings, fine-tune it, maybe go from -3 to 3 on the x-axis. While I'm in here, I could also add an x and y axis label, or for applied problems, you can type in words like costs and profit and things like that. A lot of settings in there to change your major, minor axes, and all of that. But I'll just keep this default otherwise. But now I don't have that square scaling. It allows me to see things possibly a little better. But I'll also say that these tables do a great job as well. These are really easy to make. I'm going to delete this one out and recreate it in just a second. I've got my function that's defined here. Using the edit list button, it creates this little button right next to it for create a table. And that's all I had to do. It's actually got the same inputs. It defaults from -2 to 2. Very easy to change. If you want to delete those out, you could start at -10, for example. And maybe if you want to go by 2, I'm just going to hit enter, then a -8. And we'll actually continue that pattern. Now I've got a lot more definition. And it's also got this great tool here to zoom fit. Now I don't really want to look at all that range of x values. You see that it gets very, very large, as well as very, very small when I use that large range. So why don't I go back to something simple where I just go from -2 to 2, and we zoom in, and I think that's a great view of it. You could definitely fine tune it, like I said, a little bit with that edit, with that graph settings button on the right. Either of these is fine. It just gives us a little bit different view. Now, another feature that you'll see here is all the way back at the beginning when we define the growth and decay rates. Those are used not in just the functions. Here I see my 110%, or in this case, 1 plus 3 is a 300% growth rate to be a factor of 4. It's multiplying by 4 every time. But the other thing is down below, we've got these points that are defined. You see these over here. These are potentially points from the table, but it's also been overlaid with this different looking point. Instead of just being a dot, we've actually got this extra grayed out sort of area around it that indicates that it's movable. The way I created that, I just picked a point where I wanted this to plot. I chose x equals 1 for both of them because that's always going to be in the window. And then I figured out what the y value would be just at x equals 1 using that RG within it. So I want to make sure that this changes with RG. And I don't want to use a function. I could actually just put in g of 100, or sorry, g of 1 or d of 1. But when I use this specific variable that is movable, and then also plot it with this special, I'm going to go in this edit list and look at the dot there. I've got this special tool to create a draggable point. And specifically, I just want my growth rate to be affected, that y amount to be affected. But you can also define x and y and have it be draggable in all directions. So it's a great tool within Desmos to create this interactive element. The other thing I've done to make it really dynamic, you'll see that the little label below it, decay rate and growth rate, is actually moving with the value. It contains both a label with words, growth rate, and then a formula, or just really an equal sign and a number. And that's over back on the left here. We see a label for that point is growth rate equals, and then I've got some coding here. If you want to really break down what this all means, check out other videos that I've done talking about labeling points, and I get into some details there, especially with quadratics. I have one where we look for two solutions on the x-axis for a parabola, and if you've covered that, you know that you use the quadratic formula, and you get a square root. Oftentimes we'll get irrational solutions. So I actually created a simplified label that would include a square root to be fully precise instead of rounding that off to a decimal. It's definitely pretty technical, but for the most part, you can copy and paste some of these inputs and just use these backticks to make it all happen. But check out that video if you want to dive into that. Otherwise, I think we've really looked at how these all relate, how we can affect the growth or decay of these functions. And I recommend you to dive into your textbook and connect these to those concepts. So you have homework problems where you're converting maybe a growth factor to a growth rate, and this can sort of help you pair with that material and study how it all goes together. The next topic that we've come across with exponential functions typically is transformations. I'll turn on this graph. I can go back to the default view. That might be okay, or if I expand this down, I actually have another one of these tables. If you've watched my videos, you'll see a lot of these. I really like using them just to center my view very easily there. And what we're looking at here is a function that's built up as an exponential with sort of a different format. When I did growth and decay, I did an initial y value times 1 plus a rate, which might be plus or minus. That's typically a decimal. But that turns into a factor and then it has an exponent. Here we're skipping the plus, minus, growth rate and all that, and we're just looking at it as a factor only. So if b is 2, we're doubling. B is 3, we're tripling. Now just to put it into perspective, if b is 3 and we're tripling, that's 1 plus 2 to get 3, 200% growth. So it can kind of throw you off like a growth factor versus a growth rate. That's just where I recommend, diving into your textbook and really looking at some of those processes to change back and forth. What's nice with this arrangement is we can think about a toolkit function or reference function or parent function. I've heard all of these terms for this. Essentially just a base to a power. B could be changed. I mean, that we still may think of that like a transformation. I would argue that B is kind of the first thing, the first most important thing that we want to decide on. So we set our base for our exponent. I'll just leave it at 3 for now. And we can see powers of 3 there, 1, 3, 9. It might be more helpful to go farther into that positive realm. So now I'm going from -2 to 4 on the x-axis, all the way up to 3 to the 4th is 81. Now that's my reference function. That shows me what a power of 3 graph, exponential graph, would look like. This one's that dashed red line there. Now let's go through some transformations. Back up at the top, we have the same b of x in the sort of inside of that function, but then there are two things being done. We have a coefficient a, which is going to be could be a stretch or compression factor in that y direction. And we've got a k, which really just shifts us vertically up and down. And both of those will look like a vertical change, but let's kind of check out the difference here. K is initially set to 0, and I've got that just with 1 unit increments from -10 to 10. I've added in this horizontal line. You see that y equals k. I made the line thickness a little smaller there, so that's a nice tool you can use. And that's just a dashed black line to indicate that horizontal asymptote. It's really good to get into that concept of end behavior of functions. Exponential functions definitely have unique characteristics from others. Now let's set it to a vertical shift. We'll go up 5 with the k equals 5. And I want to really kind of think of that as just the horizontal asymptote. So that k value, sort of that's hanging off that constant, that's just where it's going to settle to. Either on the negative x-axis, if it's growing, we can think of tracing it back or sledding down the hill in the wrong direction, because we always want to go left to right. So that's the growth function. We have to kind of trace it back. Or if it was a decay function, then we would be, sledding down the hill in the forward direction and seeing what we're settling into in the positive x direction. But either way, k is our horizontal asymptote. It can look like a shift up and down. But like I said, we also have this vertical stretch. And that can look like a shift up and down, but you'll notice that it's only really happening at the other end. So we can kind of think of k as affecting the baseline, where is it going to settle to? And a is going to sort of stretch it and almost like peels it away from that more as we multiply our y values by bigger and bigger amounts. And it's stretching away from the asymptote, not the x-axis. So there we see it stretching away from the asymptote. Or if we make it negative, we introduce a vertical flip and stretch it away in that y direction from the asymptote there. And all we really talk about with these exponential functions are these two vertical changes. You notice that this doesn't contain a horizontal shift or a horizontal compression or stretch. And that's one of the very unique things about exponential functions. Let's go ahead and try to shift this blue line, this transformed exponential function, to the right by 1 and see what happens. So I could introduce it as a minus h in the exponent, which is, I'm going to have to use a parentheses there to make that happen. That's a common way that we do that horizontal shift, and then just set that h to be 1. And now it should have just moved it to the right by 1, but we can set this step size to 1 and check it out. Okay, so it looks like to me, it looks like it's just peeling away more. Now, this is totally just your perspective, but you could see it as sliding, or for me, because I was just doing this, I almost see it more as that peeling away factor. Well, here's what happens. If we put a 1 in, let's get rid of it as a slider and just have it be a 1. we can actually do a little bit of algebraic simplification just by rearranging things. And maybe it would be good if I were to just copy and paste this, just make it a y. I don't want f of x to have to be defined in two different ways. So now I'm going to, I'll leave that one there. Now this, let's do some simplifying. When you have addition or subtraction in the exponent, it's actually just multiplying or dividing the bases. So this would be the product or quotient rules for exponent. What we would have is, this is the same as x times, let's see, b to the x times b to the negative 1. So we're almost splitting it apart. We maybe usually use that rule in the other direction. I think usually we'll say if we're multiplying the same base, then we can add the exponents. So that would be x plus negative 1. We used it sort of the other direction. We wanted to split that x and negative 1 apart. So we divide that into the two factors with the exponents that would add up to x minus 1. And then b to the negative 1 is just 1 over b. And each step along the way, notice how the lines still coincide. If you need a little more contrast, I can make this one dotted. There we can see the dotted line overlaying. So that just confirms that I haven't algebraically changed this function from this expression. And lastly, a over b is the same as this a times 1 over b, using commutative associative properties of multiplication there, just to do a little rearranging. And now we see that all we've really done, instead of shifting it to the right by 1, is we've reduced the stretch factor by this factor of b. We've divided out a b. So I could change this to a 2, and then it would be a b squared. I could change it to a 3, and then it would be a b to the third. But essentially what that means is a left-right shift can be changed its perspective into a vertical stretch or compression. Now, one thing that I did is I went into ChatGPT and basically just said, explain to me why an exponential horizontal shift is or could be changed into a vertical stretch. And it really laid out that process to get from where we started to where we ended, and it can actually explain that a little bit. So I encourage you to try that out if you want to dive into that tutorial a little bit more deeply. Obviously, we're kind of limited when we're just working with this Desmos input to manipulate and change these. It's definitely a lot better to have a more technical step-by-step or even a written solution for something like that. But I always love thinking about this concept. Now, if you wanted, you could also argue why we don't have a coefficient in front of the x here. That would also be something that I could simplify out. It would end up just adding complication where it's not needed. This a factor takes care of any horizontal changes that we would want to make at all. Everything could be converted into some kind of multiplicative factor in front. Other than that, I think we've talked about all the different transformations we see here. Then you can go back through all of this with just a different base, looking at a very large base, which is going to be a very steep function. And when I'm in the decimal range from 0 to 1, it's a decay function because we're basically multiplying by something that is a portion of what it was before. Here, for example, if b is 0.4, it's kind of like a 60% reduction. We take 60% off, we have 40% remaining. So we're going to look at 40%, 40%, 40%, and settle down into that horizontal asymptote when really none remains. I cannot actually go past 0. 0 to any power is still 0, and 0 to a negative power, kind of things get weird. So you might actually want to bottom this out at 0. It's interesting to see what happens when we do slide it into the negative. We'll only actually get whole numbers that'll work. Decimals aren't going to work when we have a negative number to with a radical. it's not going to quite work. But some of these end up working out because negative to an even power sends us to the right, negative to an odd power sends us to the left. So it's almost sorting out evens and odds. It's just a completely different situation than where we started with. It's kind of an interesting study how much that function changes in the negative range to then the decimal range being a decay function to 1 being a horizontal function, and then showing steeper and steeper growth from there. It's just one of the odd things about exponents. And then we find that with logarithms, when we find the inverse of these, it results in some of those same kind of oddities, but now reversing x and y. So I think this is why exponential functions are really a challenge. They're very unique in a lot of different ways. When we go from the left end to the right, it's very different behavior. We don't have that even function symmetry where we can reflect it across the y-axis. That's really nice with functions like quadratics. And this one's just very unique in itself.